Good day, mathletes. So we're going to talk about implicit differentiation today. And this is a topic that is brought to us by the chain rule. So the chain rule allows us to do implicit differentiation. And implicit differentiation is nice when you have, or is necessary even, when you have a situation where you have an equation or a curve that is in terms of two variables. And so here, like this is actually the equation of a circle. I'm not sure if you've done conic sections before, conic, C-O-N-I-C, but conic sections are circles, ellipses, hyperbolas. Parabolas are actually a conic section as well. But if you graph, and the reason they're called conic sections is because they're slices of a cone. So you can slice a cone in different ways and get each of these different functions. But if you were to graph this function here, like here on Desmos, you would see that it's a circle, right? And when I say graph this function, I should be a little careful with using the word function, because this is actually not a function, right? Because it doesn't pass the vertical line test. There would be an infinite amount of vertical lines actually that would cross more than once, and so there's more than one output for each input. So this is actually not a function. A circle is not a function, but it is a curve, and it's something that is common in our world, and something that we may want to find slopes at certain points to, or instantaneous rate of change, or tangent lines, or things like that, right? And so implicit differentiation gives us a way to do that. So back to here. So one thing I could do to solve, or one thing I could do to differentiate or to make it even a function, is I could solve for y. But if I solve for y, and I won't get into the math, I won't do all the math just to save time. But you guys know how we could do this, right? We could subtract x squared from both sides, and then we could take the square root of both sides, right? And so what we'd end up with is y equals the square root of 25 minus x squared, and then when we take the square root of both sides, we'd have to do the plus or minus in front here. But just to show you, that isn't perfect either, because then if we graph this function, we only have one side of that circle, right? We don't have the whole circle. And so that's why you would need the negative also. So you need to have two different functions in order to complete the whole function, and then you'd have two different derivatives to find, et cetera, et cetera. And so implicit differentiation gives us a way to kind of bypass that mess. All right, oops, let me go back to this one. So let's see how it works. So with implicit differentiation, what we're going to do is we are going to take the derivative of the entire equation with respect to a certain variable, and usually it's going to be x. Like here they say dy dx, so that's in terms of x, right? And so what I'm going to do is I'm going to do d dx. I'm going to take the derivative of that whole equation. So I'm going to do the derivative of x squared with respect to x. I'm going to do the derivative of y squared with respect to x, and then the derivative of 25 with respect to x. My color wheel is in the way here, but yeah, the derivative of 25 with respect to x as well. So all right, and so first of all, if we do this one, no sweat, right? We know the derivative of x squared with respect to x is just 2x. Okay, and let's do the other side. The derivative of 25 with respect to x is just 0, right? So that's not bad either. So this is where it's a little tricky, because we're taking the derivative with respect to x, but it's a y function. So what we'll do is we'll consider y as a function of x, right? We'll basically figure y as a function of x, and we'll take the derivative of the outer function, and so what we'll get is we'll get 2y But then with chain rule, we have to also take the derivative of the inner function, which is some function of x, right? Which we don't know exactly what it is, but we can just say, okay, well, it's just going to be times y prime, right? Or if you use Leibniz notation, dy dx, okay? But I'm just going to do it as y prime because it's just a little easier to solve for, okay? Even though here they say find dy dx. So basically we're using the chain rule. So this is the derivative of that inner function that we don't know, right? We don't have y solved for x, so we're just going to call it y prime. Okay? And so then from there, now if I want to find dy dx, I can just solve for y prime. So what I'm going to do is I'm going to subtract 2x from both sides. And we'll get 2y times y prime equals negative 2x, right? Write that down here. And so now all I have to do is just subtract, or divide both sides by 2y. And now I have y prime all by itself. So it's going to be negative divided by negative is a positive. 2 divided by 2 cancels out. So it's just going to be x over y. And so this is the derivative dy dx. Okay, so dy dx equals y prime equals x over y. So here's another difference with this is now we have a derivative, a dy dx, that is in terms of two variables. So if we want to evaluate this at a given point, we have to know not only the x but the y, right? So we can't just, it's not just plugging in a value for x. We have to plug in a value for x and y if we want to find the slope at a given point, or the tangent line, or the instantaneous range at instantaneous rate of change at a given point. So, all right. So and this is part of what it's saying here is that the result, the answer is in terms of the independent variable and the dependent variable, right? And sometimes we can get it in terms of only x, but a lot of times it's not. That's not the case. It's not possible to do so. Okay. All right. So here's our answer, and you don't necessarily have to write. You can just write y prime. That's fine, but just remember that y prime dy dx are the same thing. I think you already know that by this point.